I hope all of you are doing well and welcome to our Applied Electricity video series. Today we'll be taking you guys through Kirchhoff's laws, which is the Kirchhoff current law, commonly known as KCL, and the Kirchhoff voltage law, known as KVL. And after taking you through and explaining the concepts well to you, we'll take you through some tutorial videos and some examples to solve problems to really understand, to enhance our understanding. And if you have any further questions, please kindly feel free to leave a comment, like, share, and subscribe to our channel so that we'll know the kind of content you really want. Thank you. Kindly stay tuned and enjoy the show. Bye. We are first of all looking at Kirchhoff's current law, and as we already know from our SHS schools, we say Kirchhoff current law simply means the sum of currents entering a node is equals to the sum of currents leaving a node. And since we know that, we'll use that definitions to now apply in circuits. So as an engineer, you don't just need only definitions, you should know how to apply those definitions in real life problems. So let us take this circuit to analyze. We are going to use KCL to analyze this circuit. So realize that KCL says the sum of currents entering a node equals the sum of currents leaving a node. So what we simply do here is to find the sum of currents entering and the sum of currents leaving. So to find the sum of currents leaving, let us look at the currents leaving. We have I1, which is entering. First of all, look at the currents that are entering into this node. This is the node we are considering. So I1 is entering, I3 is entering, and I5 is entering. So we can write it down. We can say the sum of currents entering. So which is I1 plus I3 plus I5. Then we also come and find the sum of currents leaving, which currents are leaving. So we realize that the currents that are leaving are I6, I4, and I2. So also write it down. And now we have to apply the KCL. How do we apply it? We simply said the sum of currents entering a node equals the sum of currents leaving the node. So we can simply write it like this. So I1 plus I3 plus I5 is equals to I2 plus I4 plus I6. So in exams, no one will be there to tell you that the sum of currents entering the node is equals to the sum of currents leaving the node. And in exams, no one will ask you to state KCL or KVL. No. They only give you a problem and they will expect you to be able to apply the concepts just as we analyze the circuit here. So in exams, maybe they can give you all the values. Maybe they can give you I1, I2, I3 and leave only I6 out, and they will tell you to find the value of I6, but they will not tell you to use KCL or KVL. So in exams, that are how some of the questions will come. So let us take some examples, then we'll know how we solve questions using KCL. So we take our problem 1. So problem 1 says we should find the value of I2 and I4 in the figure below. So what do we first do? We have to identify the nodes, because KCL simply means, you see, they didn't tell us that we should use KCL here. You see, that's how the questions will come. Simple find the value of I2 and I4. So here we have to identify the nodes so that we now use KCL. So I've identified one node here, which is here. That's why I'm circling, and I've identified another node, which is here. So let's name the nodes A and B. So I'll name here A, then come and name here as B. So we'll now do our analysis. So I will say at node A, we are going to apply KCL. So at node A, we realize that I1 is entering, which is equals to 6. I1 is entering, and since I1 is entering, we also come to this side and we see that I2 is leaving and these two arms is also leaving. So we can simply write that 6 here is equals to I2 plus 2. So here we simply do change of subject to get I2. So we do 2 here is equals to 6 minus 2, which is equals to 4 amps. And we found I2. We now know the value of I2. So we now come and also find the value of I4. And we know that we will say at node B, let's look at all the currents that are entering. Realize that I2 is entering at node B and I4 itself is also entering. It's only I3 that is leaving, and they've given us the value of I3 as 9 amps. So we simply come here again and we say I2 plus I4 is equals to 9. And already we know that I2 is equals to 4, our 4 here. So we can simply say our I4 here is equals to our 9 minus 4. So we have I4 here is equals to 5 amps. And we are done. We are done applying our KCL. And we will realize that this is just a simple question that you just need seconds to solve. So let us take another example to really understand the concepts well. So moving forward, we should find the value of I1, I2 and I3. I1, I2, I3 and I4 in the figure below. Since I think you've already observed, they don't tell us that we should use KCL or we should use KVL. You have to know what to use. So KCL is used for current. It's used to calculate currents at a node, and KVL is also used for something else. So no one will tell you what to use here. You are the engineer here, so they expect you to figure out. So realize that they're asking us to find the value of these 4 currents, which is I1, I2, I3 and I4. So first of all, identify our nodes as usual. So I'll use different colors to figure out the nodes out. So we'll identify our first node, then we'll name it A. Then we'll identify our second node and we name it B. We identify our third node and we name it C. We identify our last node, our fourth node, and we name it D. So now let us analyze each node in order to be able to find all the currents they've given to us. So let us look at node A. So at node A, realize that the currents entering, which currents are entering? We have this 10 amps which is entering. We have this 1 amp which is also entering. And we have 7 amps leaving and we have 5 amps leaving. So we say sum of currents entering node A is equal to sum of currents leaving node A. So we found those that are entering. So those that are entering are 10 plus I1, which should be equals to sum of those entering, leaving, which is 5 plus 7. So here we simply do change of subjects. So our 5 plus 7 is equals to 12. So we say I1 here is equals to our 12 minus our 10, which is now equals to I1 will now be equals to 2 amps. So realize that I1 is now equals to 2 amps. Then we found I1. Let us now find I2. So I2 here at node B. So at node B, we have to find the currents entering and the currents leaving. So we have this current which is leaving I1, this current which is leaving, which is also 1 amp, and we have I2 which is also leaving this node, which is unknown, and we have 5 amps which is entering. So we now have to sum all those entering and those leaving. So we find out that 5 is entering. So we have our 5 here. 5 here should be equals to all those leaving. So I1, we already know the value of I1 as 2 plus 1, then plus I2, which is also leaving. So simply here we do our change of subject, then we get I2 is equals to 5 minus 3. So we equally get I2 is equals to 2 amps. I always remind you the units are very, very important. We need them. So we also now analyze node C. So we say at node C, we realize that I2 is entering node C, and I3 is leaving, and 6 amp is leaving, and 8 amp here. Let's look at, okay, first of all, let's look at the currents that are entering. 8 amp is entering, and I2 is entering, and I3 and 6 amp are also leaving. So let's analyze that one. So those that are entering are I2, which we know it to be 2. Those are those entering. So we have our 2 plus our 8 here should be equals to those leaving. Those leaving are this and this. So we have our I3 plus 6. So we can say I3 here is equals to the 10 minus the 6. So 2 plus 8 is 10. So we have 10 here minus 6. So our I3 here is equals to 4 amps. Then we now calculate for our I4, which is at the node D. So for node D, at node D here, so at node D, we realize that the 6 amp is entering node D, and the 12 amp is entering node D. Let me use the highlighter. We realize that this arrow is entering, this 12 is also entering here. It's only I4 and 8 that are leaving. So let us sum them up. Which ones are leaving? Those that are leaving are I4 plus 8 is equals to our 12 plus our 6. So 12 plus 6 gives us 18. So our 18 here, we say I4 here is equals to 18 minus 8. So finally, we get our I4 as 10 amps. And it's as so simple as that. So basically, this is how we solve KCL questions. And if you're able to identify the nodes, you realize that the important thing here is to identify the nodes, then you are good to go. So I think we are good to go here, and we'll move on to KVL. Kirchhoff's voltage law. And Kirchhoff voltage law states that the algebraic sum of voltages in a loop equals 0, or we can also state it as the algebraic sum of voltage sources is equals to the algebraic sum of voltage drops. So let us use some diagrams to explain it. So let us look at something here. This is one important concept I want you guys to really understand. So we see that from this circuit, when we move from minus to plus, that is a rise in voltage. We have to represent this as a plus voltage, because it has moved from a lower potential to a higher potential. That means there has been an increase in the potential. Then in this circuit too, when we move from a higher potential to a lower potential. We call it a fall in voltage because we move from a higher potential to a lower potential. And knowing these things will really go a long way to really save you, because in some of your analysis, especially if you want to use the first definition, the algebraic sum of voltage is in a closed loop equals 0. You will really make use of these two analysis I've kept here. You really need to make good use of them, because if you don't really understand these concepts well, you end up by getting the right getting your final answers wrong, because this one really confuses a lot of students. And as we go on, I'll use a question to really explain how these things work over there. So let us look at voltage drops, because what does voltage drop mean? So with voltage drops, I want to apply KVL using the second definition. They said the algebraic sum of voltage sources equals the algebraic sum of voltage drop. So when we look at this circuit, how many voltage sources are here? We have only one, which is this voltage. So they said the algebraic sum of voltage sources is equal. So I've identified my voltage source, which is V, should be equals to the algebraic sum of voltage drop. So what does a voltage drop means? It simply means that anytime current flows through any resistive element, or there will be a voltage drop, because let's say if there's current flowing from this circuit, if current is flowing from this source, this volt, when it gets here, there will be a voltage drop, and the voltage drop will be represented by the current multiplied by the resistance. So here the voltage drop across this resistor will be I times R1, and the voltage drop across this resistor will also be I times R2. You see, you realize that the voltage drops here might be different depending on the value of the resistor here, because if this is a large value, the voltage drop here will be large or smaller. So basically, that is one thing you need. So if the resistor value here is large, then that means the voltage drop here will be large. If it is small here, the voltage drop here will be small. So it simply means, current wants a free path. So the voltage drop will simply here tell you that the kind of stress the current will have to pass through before passing through the whole the circuit. So using our second definition, they said the sum of voltage sources equals the sum of voltage drops. So which are the voltage sources? These are our voltage sources. That's why I've written it here. Then let us also look at our voltage drops. This is our voltage drop, and this is a voltage drop. They said the algebraic sum of voltage sources. Since we have only one voltage source, that's why we only wrote one. We have one voltage source here, should be equals to the voltage drop. So we have our I times our R1 plus our I times our R2, and we know that from Ohm's law, V is equals to IR. So that is why we call I times R a voltage drop, because it's simply a voltage, but it is from the source that has been dropped. So basically this can also be called voltage. That is why the first definition, they said the algebraic sum of voltages in a closed loop equals to 0. And here they said you can also state it as the algebraic sum of voltage sources is equals to the algebraic sum of voltage drops. So basically this is the equation we can use to solve the question here, this circuit. So basically that is how we apply KVL, and I want to take an example so that we'll really use this example to solve a question here. Then we will know how things go from here. Thank you. 3 says find the value of I in the circuit below, and we realize that I is the current that is passing through the branch D and E. So we have to find the current passing through this. To find the current, we first of all analyze the circuit. So let us say the current that this 12 volts power delivers is called I1. the same I1 comes here. Then the current that this 6 volts delivers is called I2. So applying KCL at node B, we realize that they said sum of currents entering is equal to sum of currents leaving. So it will be I1 plus I2. And realize that the same current is entering node C. So let us also say the current that is being delivered by this 24 volt is Y. Then realize that the current that is being delivered, the sum of I1 plus I2 plus Y enters node C, and this, when you sum them, when those things are summed up, the same, they leave that branch to form the I. So basically this is what I mean. So sum of currents entering, so we see that this one is entering, this one is entering, so they combine here, then the sum of those entering is equals to the sum of those leaving. So basically we can apply KCL at node C. So applying KCL at node C, we get Y here plus I1 plus I2 is equals to I. So making Y the subject, Y is equals to I minus I1 minus I2. Then we'll take our loop around to find the current in this branch. We'll perform KVL in all the three. Perform KVL in all the three loops. So performing KVL in the first loop, we have to perform KVL in this first loop. We will realize that performing KVL, we said KVL says sum of voltages is equals to sum of voltage drops. So let us look at the voltages here. The first voltage is 12, which is moving from a lower potential to a higher potential. So meaning we have a positive 12 here. Then when you get here, it is moving from a higher potential to a lower potential because we are moving in the clockwise direction here. The clockwise direction. So coming from the clockwise direction, meaning it's moving from a higher potential to a lower potential, making it negative. So we have our 12 here minus 6. Then let us look at the voltage drop. Voltage drops are 6I1 because wherever there is a resistor, that is where we consider it to be a voltage drop, because when this current gets here, this one will basically become a voltage drop because voltage is equals to IR. Current times the resistance. So voltage drop will occur here and another voltage drop will occur here. But let us look at the direction. We realize that we are going in a clockwise direction, and going in a clockwise direction, this current is going in a clockwise direction, so it will be 6I1. Then we realize that I2 here is going in opposite to our direction, which is an anti-clockwise direction, so it becomes minus 6I2. So our voltage drops becomes 6I1 minus 6I2. Then after solving it, we get 1 here is equals to I1 minus I2, which becomes our equation 1. Then we also apply the same KVL as I said in the next loop, applying it in B, C, F, G, B. Realize that when we start, let's look at the sum of voltage sources. So sum of voltage sources is 6 and 24. So we see that with 6 we are moving from a lower potential to a higher potential, and we are moving in the clockwise direction. And realize that when we get here, we're moving from a higher potential to a lower potential, so making here minus 24. So here we get the voltage sources are 6 minus 24 here should be equals to voltage drop. And look at the voltage drops, we're moving in the clockwise direction, so it becomes 6I2 plus, this one is also moving in the clockwise direction, 3 times I1 plus I2. Then we come here, we're moving in the clockwise direction, but Y is going in the anti-clockwise direction, so it becomes minus 12Y, and we know the value of Y, which is I minus I1 minus I2. So our voltage drops now becomes 6I2 plus 3 I1 plus I2 minus 12 I minus I1 minus I2. Then after solving everything here, we get our answer as minus 18 is equals to 22I2 plus 15I1 minus 12I, which becomes our equation 2. Then we also apply KVL at the last node. So applying KVL at the last loop, we realize that we are going in the clockwise direction here too. And going in the clockwise direction, what do we realize? Realize that the voltage source here is 24. We only have one voltage source if we are considering this last loop. So we are moving from a lower potential to a higher potential, which makes it a positive voltage. So we have 24 equals to voltage drop. Our first voltage drop is this 12 times y, which we know our value of y as this. So just substitute 12 times y, which is going in the clockwise direction, plus this is also going in the clockwise direction because you see the arrow of the current is here. So this 2 and this 3 are in series. We can just combine them to become 5, but because I want to do it for you to understand, I'll do them separate. So we have 2i plus 3i because all of them are in series and they are all going in the direction of our current. So we now write it as 12y, which y is equals to I minus I1 minus I2 plus 2i plus 3i. So at the end we get 24 here is equals to 17i minus 12i1 minus 12i2, which this becomes our equation 3. So we simply now solve the three equations simultaneously. And after solving them simultaneously, we get our I. They told us that we should find the value of I. So we get our I as 1.58 amps and I1 as 0.62 amps and I2 as minus 0.39, approximately 0.4. So the current that we're looking for is I, which is 1.5 amps. So basically this is how we solve the KVL questions, and you realize that with KVL no one will come and tell you that use KVL or not, use KVL or use KCL. See, you are the engineer here, you are the one in control. So basically you will know what to use and what not to use. So thank you. Our last problem on this video series, we have problem 4. So with problem 4, they said we should find the currents in all parts of the circuit. So what do they mean? This meaning we should find all the currents in this circuit. So we should find I1, I2, I3. So to find I1, I2, I3, we'll have to perform KVL and KCL. So we realize that A, B, C, D, A is one loop, and C, E, F, D, C is also another loop. And here the good thing is that they've done our current assignment for us. So since they've done our current assignment for us, we just we'll take the loop in a clockwise direction, and here we'll decide to take the loop in anti-clockwise direction. So writing KVL for this first loop, KVL says sum of voltages in a closed loop is equals to 0. I'm going to write it in the two ways that they stated it. So sum of voltages in a closed loop is equals to 0. So we know that this is the voltage. We know that this is also a voltage drop, but when we multiply I times R, it becomes a voltage drop. This is also a voltage drop. So we can write it as 32 minus, because it's a voltage drop, that's why we are all voltage drop, we always negate them, minus I2I1 minus 8I3. We can write it as this: 32 minus 2I1 minus 8I3 is equal to 0. It can be written as this. And after writing it as this, We can also write it as the second way when they said sum of voltage sources is equal to sum of voltage drops. So the voltage source here is only 32 and the voltage drops are 2I1, and since we are moving in the clockwise direction, we see that this is going clockwise. This current I1 is going clockwise, I3 is also going clockwise, so meaning they are all positive. So 32 is equals to 2I1 plus 8I3. So the voltage source, they say sum of voltage sources is equals to sum of voltage drops. And basically that is our equation. We are done with this first loop. Then we go to our second loop. The second loop says the second loop, considering the second loop, we realize that we are moving in the anti-clockwise direction. And they said algebraic voltages in a closed loop is equals to 0. So this is the voltage 20 minus 4I2 minus 8I3 is equals to 0. That is one way we can write it. Or they also said sum of voltage sources is equal to sum of voltage drops. So the voltage source here is 20. Then we can write our 20 is equals to voltage drops. So voltage drops here is going the anti-clockwise direction. All the currents too are going in the anti-clockwise direction, which is 4I2 plus 8I3. So we'll write it as 20 is equals to 4I2 plus 8I3. Basically, we'll write it like this. After writing them like this, realize that we have our two equations, but there is left one thing. We have to apply KCL at node C. So applying KCL at node C, we realize that KCL says the sum of currents entering is equal to the sum of currents leaving. So we see that I1 is entering node C, I2 is entering node C, and I3 is leaving. So we can say I3 is equals to I1 plus I2. So when we apply KCL at node C, this is what we get. After getting all these three equations, we solve them simultaneously using our calculator. And I know that all of us know how to do it. If you don't know how to do it, the next video I'll record a video on showing how to solve this kind of equations using your calculator within seconds. So after solving these equations simultaneously, we get our I1 to be 4 amps and I2 minus 1 amp and I3 as 3 amps. So basically this is how we solve KCL and KVL problems. Kindly like our videos, share, subscribe. I know this video has been very helpful. Share to your course mates, subscribe, leave a comment. Let me know where you don't really understand, then I'll explain it to you. So thank you for staying tuned up to this time, and thank you for watching. Please like, share and subscribe. This video was being covered by Atiigah. You can reach him on this number. Thank you very much.